Here we are asked to find an expression for the expectation of y as an integral, which can be unsimplified. Just keep it as it is, basically. So z is a normal, standardized normal distribution, random variable taken from the standard normal distribution. Y is the max of z and 0. And so let's think about what this means first of all. So let's draw the PDF of z, something like this, right? So it goes up here and goes down like that. Okay, well, it's a little skewed, but it should be normal. So sorry about that. So this is 0, this is z, and y is the max of z and 0. So this means that when this random variable, when z is in this region, y just takes on the value of z. Yeah. So if z ends up being a, well then y ends up being a. However, if we end up in this region here, this side, y will take on the value of 0. So you can never take on negative values. That's what this part here means. Okay. Now we're asked to find an expression for the expectation of y. So let's write this down. Expectation of y equals by Lotus. We can use the PDF, the distribution of the original random variable. That's what Lotus means. And z is standardized normal. So this is the PDF over y over the full support of z. So let's work a little bit with this. So y we know is the max of little z 0, the PDF of y, and this we can write as, because we're always taking on values larger than 0, this integral ends up being the integral from 0 to infinity, where we can write this piece here as z over the PDF of z, and then take dz. So we're taking the integral over z. Okay. Let's now move on to this part. Here we are asked the following. So we have y1, y2, a set of infinitely numbered many random variables y that each has they have the same distribution as y here. So we're going to let this n be the minimum of all these indices of n. So it's the smallest value, such that when y1 equals 0, n takes on this index. So the logic here is that we're drawing for each y, we're drawing from this distribution, and once it hits below this in this region here, and takes on the index of that random variable. So let's write it down. So this is think about them as an ordered set of series of random variables. It goes on and on, and whenever one of these guys end up being here, n takes on the value of this index here. Okay, so And what is that? So that is basically a first success distribution, and it's first success because, again, it's all about keeping track of when any of these y's take on the value of 0. So you're going to write n as being distributed as first success with a probability p. And what is this probability? Well, it is half here because the PDF of Z, half the mass is to the right of 0 and the other half is to the left of 0. And so Z will always take on probability half positive values, probability half negative values. Okay, so let's now take the figure out the expectation of n, and now this is a discrete random variable starting at 1, right? We're counting the success up to infinite number of values, so y, and then the probability of n taken on j. Should be j here, right? So this is j, not y. Okay, and the PMF of n. The PMF of n is, well, we don't have to. I mean, we could just write it out so to be explicit, and then we won't derive the full thing. But the PMF of let's do this 1 like that. J, and the PMF is 1 minus P, and we have P there, that's a 1, and that's it's like that. So the expectation of n, then if you expand this, we'll do this in another video where we derive the full thing, will be the expectation of the geometric plus 1. So the geometric is q divided by p plus 1, because we are starting at 1. We're adding the success to the geometric, which starts at 0. And q is 1 minus p. So that's half. The other one is a half too, and that's then the 1 there, and the whole thing evaluates to 2. So that's the expectation of n. So you have to flip y 2 times an expectation to end up to the left. Negative values. Okay, so let's move on to the last part of the question here. Here we are asked to find the expectation, the CDF of y. Okay, the CDF of y. Let's think about that. The CDF of y. Whoops, CDF of y. So I'm just going to write down, this is the CDF over y. The py less than little y. I'm going to insert the definition of y, which is the max random variable z, 0 less than y. And now we think about what this max of z, 0 less than y means. Well, that is the same thing as z being less than y and this y being larger than y. Okay, and so this in turn we think about what it means, and so this means that, and now I'm going to write y, so for the values of over the real number line, this is probability here. And so when y takes on negative values, let me copy this piece here, copy this, paste it in here. So when y takes on values here, so it's negative, well, we'll see that this event here says that cannot be true. Well, y has to take on values larger than 0 in order to this event to have positive probability. So it means that when we are in this region, negative region, the whole probability, the CDF, evaluates to 0. And so when y is equal or larger than 0, this whole thing will evaluate to the CDF of a standard normal. And why is that? Well, we said that y will always take on values that, say, imagine that, I mean, we had a here, any value, positive value. Well, what's the probability? What's the CDF? What's the probability for y happening? Well, that is evaluated as the CDF of z of y. And so that's the probability it will take on. So that's the CDF of y.